In this lesson, which is section 11.4, we're going to move from just using our counting principle and permutations and combinations to count different ways that things can be arranged, and we're going to actually look at probability. And there are two slightly different ways to talk about probability. One way is called theoretical probability. Now, we're going to call an event E, and that is the thing that you're checking the probability of, like rolling a 6 or flipping a coin and getting a heads. Those items are the event. If an event has N of E equally likely outcomes, like rolling a fair die, it is just as likely to be a 6 as it is a 2. And its sample space S, and that is all the different things that can happen, has NS equally likely outcomes. So E is the number, N of E is the number of equally likely outcomes of the event. Well, we'll talk more about that. That's for the event to happen. The sample space is all of the different things that can happen. So if you're rolling 2 die and you want to say, what is the probability of getting a 5? Well, getting a 1 and a 4 gives you a 5. Giving you a 2 and a 3 gives you a 5. Those are both events. But rolling 2 dice gives you lots of different things, and that's the sample space. All right, so the theoretical probability of an event E, denoted by probability of E, P of E, is the number of outcomes in the event, the number of ways the event that you are testing can occur, divided by the total number of possible outcomes. All right, that is theoretical probability. Empirical probability, this has to do with observing something, like in an experiment. In this case, it would be observed number of times E occurs over the total number of observations. Okay, so this is a little bit more experimental, whereas this happens in theory. All right, let's see how to use these and which one we're using. All right, we're going to use on the first few problems theoretical probability. All right, problem number 1. It says if a 12-sided die is rolled, the set of equally likely outcomes is 1, 2, 3, 4, 5, 6, 7. This is the sample space. That is everything that can happen. Find the probability of rolling a 9. Now, if I look at this, I know that the probability is the number of ways I can get a 9 on top over the total number of things I can get. There are 12 outcomes. When you roll this 12-sided die, you could get a 1, a 2, a 3, a 4, and so on. That's your sample space. How many different ways can you get a 9? Well, there's only one, rolling a 9. The probability in fractional form, because they say is an integer if it happens to go in evenly, or a simplified fraction, it is 1 out of 12. Theoretically, if you roll the dice 12 times, you should get 1 9. Now, you really might not, but that's what the theory says. Number 2, a 12-sided die. Here are the equally likely outcomes. So once again, they're giving us the sample space. That's always the denominator. Find the probability of rolling a number less than 9. Okay, well, the probability of less than 9 is, okay, sample space is 12. How many ways are there to get a number less than 9? Well, you could get an 8, a 7, a 6, a 5, a 4, a 3, a 2, or a 1. And all of those would satisfy less than a 9. How many of those are there? There are 8. It asks for a simplified fraction. Divide each of those by 4, and I get 2/3. Theoretically, if I roll it 3 times, 2 out of those 3 times, I should get a number less than 9. I might not, but that's what the theory says. All right, let's look at number 3. A 12-sided die is rolled. The set of equally likely outcomes is, and we have that same sample space. Find the probability of rolling a number greater than 4. Okay, so the probability of greater than 4 is, well, sample space on the bottom, there are 12 outcomes. Greater than 4, that would be 1, 2, 3, 4, 5, 6, 7, 8. There are, once again, 8 ways to get a number greater than 4. So this probability is also 2/3. All right, number 4. We're rolling a 12-sided die. Here's the sample space. Find the probability of rolling a number greater than 19. Okay, probability greater than 19. Well, the sample space is still 12. How many ways are there to get a number greater than 19 from this one die? And the answer is there aren't any. It is 0. The probability of this happening is 0. All right. I think we're going to leave the 12-sided die and go to some cards. It says you are dealt 1 card from a standard 52 card deck. Hopefully you are familiar with a 52 card deck that has 4 different suits and 13 cards of each suit, ace through king. Find the probability of being dealt a 10. Okay. Probability of a 10. All right, the sample space. If you are dealt 1 card, how many different things, how many different cards are there? Well, the sample space is indeed 52. There are 52 cards. What is the probability that it is a 10? Now you have to know just a little bit about the cards, and it is a traditional poker deck. And how many 10s are there? Well, there's 1 for each suit, so there are 4 of them. The probability is 4 out of 52. Reduce it to simplest terms, that is 1/13. The probability of getting a 10 is 1/13. Okay? Number 6, you are dealt 1 card from a standard 52 card deck. Find the probability of being dealt a heart. Probability of a heart. Well, there are 52 cards, again, 52 different cards. How many cards are there that would satisfy being a heart? Well, there are 13 in each of the suits, so 13 out of 52, and that reduces to 1/4. 1 out of every 4 cards, if you were dealing, should be a heart, theoretically. Okay, number 7. You are dealt 1 card from a standard 52 card deck. Find the probability of being dealt the 10 of clubs. All right, probability 10 clubs. Well, there are, again, 52 cards in the sample space, 52. How many 10 of clubs are there in the deck? How many different ways can you get 10 of clubs? Well, there's just 1. That's reduced to lowest terms, and that is the probability. All right, let's look at number 8. We are still working with theoretical. A fair coin, and that means one that is equally likely to be heads or tails, is tossed 3 times in succession. Okay, so you flip it, you flip it, you flip it. The set of equally likely outcomes is, and this is your sample space. You might get head, 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 tail, head, tail, head, and so on. Find the probability of getting exactly one tail. Probability of one tail. Well, you know that the sample space goes on the bottom. And how many outcomes are there? 1, 2, 3, 4, 5, 6, 7, 8. There are 8 outcomes to flipping it 3 times. What's the probability of getting one tail? Now, I wished it had said, we're going to have to take it literally, one and only one tail. Okay, so this outcome gives us one tail, this outcome gives us one tail, and this outcome gives us one tail. So the probability of getting one tail is that event occurs 3 ways. So the probability is 3 out of 8. Okay, let's look at number 9. It says, once again, a fair coin is tossed 3 times in succession, and the set of equally likely outcomes, the sample space, is right here. Find the probability of getting exactly 2 heads. Okay, probability 2 heads. Well, the sample space, the total number of outcomes is, again, 8. There are 8 different patterns you could get tossing it 3 times. How many of those have 2 heads? Well, there's one, there's one, there's one, and that's it. So that would be 3 out of 8. Okay. Number 10. A fair coin is tossed 3 times in succession, and so on. So this is starting out the same way, and again, this is your sample space. Find the probability of getting a tail on the first toss. Okay. Probability tail first. Well, there are 8 possible outcomes. Tail first. Let's see. This is a tail first. This is a tail first. This is a tail first. And this is a tail first. So if you have your sample space written down, these theoretical probabilities are not that hard because there are 4 ways for that event to occur. 4 eighths reduces to 1/2. Kind of makes sense. For any toss, there should be a 50% probability of getting head and 50% for getting tail. So that really shouldn't surprise us. All right, now we're going to move into empirical, where we are making our decisions based on observations, not just based on the number of ways things can happen. So in one way, this might be a little bit more involved. Let's take a look. This problem involves empirical probability. The table shows the breakdown of 95,000 single parents on active duty in the U.S. military in a certain year. I don't know if we'll need this, but I know that there are 95,000 single parents in the military. All numbers are in thousands and rounded to the nearest thousand. So in other words, If I see 26, this is 26,000. It might have started out being 26,215, but it rounded to the nearest thousand, 26. Use the data table to find the probability that a randomly selected single parent in the military is female. All right, let me get to something. There we go. Randomly selected parent is female. All right. Well, the probability is the number of females over the total number. It really works the same way. All right, what is the total of all of the parents, the single parents? We look at this for a minute. This is male, single parents, Army, Navy, Marine, Air Force, total male. Female, 10, 7, 1, 6. In the different branches, total of 24. Total Army, right here. Total Navy, right here. Total Marine, total Air Force, total. Okay. The sample space was actually given up here. It is down here. Calling it the sample space, that's not quite accurate. The total number is 95, and I will remember that it is 1,000. How many observed or documented were female? Well, the total female are right here. So it is 24 out of 95. If you had wanted to, you could have added 36, 37, 22. That would give you 95. And you could have added 10, 7, 1, 6. That would have given you 24. But I did it in one. Now let's see. Type an integer or a decimal rounded to the nearest hundredth as needed. So I need my calculator. Okay, I have 24 divided by 95, and it says round to the nearest hundredth as needed, so the 2 is going to say to leave this, so this is 0.25. As a percent, it does not ask for a percent, but as a percent, it would say that about 25% of these single parents are female in the military. All right, let's look at the next one. We still have 95,000 single parents on active duty in the military, so on and so forth. And we're supposed to find that a randomly selected single parent in the U.S. military is in the Army. Okay, from the data we're given, from these observations, there are still 95,000. Oh, and let me go back for a minute. Because this was 1,000 divided by 1,000, the thousands divided out. That's why I didn't address it. If you had had both of these as 1,000, those would have divided out. Okay, so they became irrelevant. All right, how many single parents are in the Army? Looking at our chart, Army, not any particular, not male or female, but total is 35. Once again, it wants this as a decimal. So I have 35 divided by 95. And this is going to round up. So this is approximately 0.37. 37 out of 100. It's more than a third, but it's less than a half. All right. Whoops. Once again, I have unfortunately lost some questions. we're going to use this same table, and if you have the notes, you've got this. So all the same stuff would start, and it would say, find the probability let me grab the piece of paper I have that has these written out. Sorry for the pause. Okay. Find the probability of that a randomly selected single parent is a woman in the Air Force. Of a woman, whoops, goodness, in the Air Force. All right, so I can use my chart. The probability of that, well, there are still 95,000. Going back up here, I don't need this anymore. A woman in the Air Force. Well, how many women are in the Air Force? Are y'all seeing 5? Okay. Okay, according to this data, it would be 5 out of 95. Which is 0.05. I will tell you that in your notes, and I apologize for this, this is the one problem, number 13, where the chart is different. And in the chart, the total number of women in the, just women in the Air Force is 4. And the total single parents is 88. So if you were to look at the printed notes, this probability would be 4 out of 88. So I am sorry. For some reason that question didn't get copied over, and I assumed it was the same data, and it's not. It is interesting, though, that it's still 0.05. Okay, so that was just a big mistake on my part. This works for what I'm talking about if you use this data, but the data is different in the printed notes. All right, after feeling kind of bad about that, I went off and I got the chart that was number 13, so I don't have to use this bad data or the data that isn't appropriate. This was supposed to be the question right here. There are 88,000 single adults, single parents, and a woman in the Air Force woman, there it is. So that's where I got the 4 out of 88. So I am sorry about that. In this last one, where we're going to use, once again, empirical, where we're just looking at our data and seeing how many times something occurred. Not what we predict, but really how many times something occurred. We don't have totals here. It says, the table shows the number expressed in millions of citizens who moved in 2004. Categorized by where they moved and whether they were an owner or a renter. Okay, so moved to the same region, moved to a different region, and this is in a certain country. I don't know any more details about it. Moved to a different country. Okay, owners, renters. Find the probability expressed as a decimal rounded to the nearest hundredth that a randomly selected citizen who moved in 2004 was a renter. Now, all of these people moved. So, the probability of being a renter, how many citizens moved? That's going to be my denominator. I have to add all of these up. So, the first thing I have to do is add them up, because I don't have any total columns like I did up here in the single parent military. Okay, so I'm going to add 11.6 plus 2.8 plus 0.4 plus 18.7 plus 4.6 plus 1. You could put 1.0, but it's 1. There were 39.1 million citizens who moved. All right, now those who moved, how many were renters? Well, it looks like I need to add these up to be just renters. So remember, the denominator is the total. The numerator is the number that satisfies the condition that you've been given. So I will add now 18.7 plus 4.6 plus 1, which is 24.3. Okay, this is renters. This is everybody that moved. So 24.3 divided by 39.1. And I'm supposed to round to the nearest hundredth. I'm sorry. And so that is approximately 0.62. So with empirical, we don't have a sample space, we have data. This is the total number. This is the number that satisfies our condition. Up here, this was the total number. This was the number that satisfied our condition. Total number, number that satisfied our condition. Whereas with the theoretical, it's how many ways something could happen, total, over how many ways the outcome that you want could happen. This is all theory. This is observation. It is empirical. Okay? You got a few problems to do on theoretical and empirical probability.